Hello, everybody. Thank you for joining again. So I'm here with Jeremy, and today we're going to go over the energy saving algorithm that we've embedded in the Wizata platform. So there's a demo out there that you can have a look. It's a quick overview, 2 minutes, not more. But today the goal is that we dive in and we can explain further how this works. But before we get into that, I want to explain a little bit why we're working towards this and how this is important for today's market. So sustainability has been a hot topic in the last many years, specifically for the heavy industry, because they are big consumers of energy and they also produce a lot of CO2 emissions. And it can be complicated if they want to improve those CO2 emissions, specifically due to new regulations, to stakeholders that they want the change, and the governments and so forth. So it's not an easy process, and you have to understand that these heavy industries, they use machines that's been running up for 30, 40 years, even sometimes more. And if they invested in these machines, let's say 10 years ago, they're not going to change the overall process. We are seeing new initiatives like green cement, green steel, that are made using other sources of resources, such as hydrogen, or maybe something different than coal that has a bigger impact in CO2 emission. And that's obviously something good, but this change takes a lot of time and it's very expensive. As I said, imagine that you are a heavy industry and you just invested 10 million in your machine, in your, vertical kiln, in your rolling kiln, or in your blast furnace 10 years ago. You're not going to change that right now, right? So, but you can start doing things with your data to start being more efficient, to reduce energy. So that's what we're going to talk about today. Like, sustainability is not only CO2 emissions. There's also other factors that play a critical role in sustainability. That could be waste management, like if you reduce waste, or if you use more circular economy, if you use more recycled products, for example. So that's why in steel, electric arc furnaces are being more and more implemented over the world. So for example, here ArcelorMittal has, I think, 3-4 plants in Luxembourg. They used to have many different blast furnaces sites, and now they only have electric arc furnace, because our electric arc furnace uses scrap or sponge iron in order to produce the steel, the melted steel that then they continue for casting and so forth. But that's a way that they reduce, let's say, the carbon footprint that these factories produce. However, they still need a lot of energy in order to melt the metal, because it uses electricity and what else, Jeremy?
No, mainly electricity.
Mainly electricity, there you go. Just wanted to double check. He's a smart guy, as you can imagine. So it's reducing waste, using a circular economy, also maintaining high output of quality. If you have a constant quality, that means that you don't have to reprocess, which is kind of tied to waste, but obviously having a good quality overall, your process makes your process be more efficient. That means that you don't have to shut down or like relaunch, and that sometimes can consume a lot of energy. And then another thing can be also the yield of your machines. If you take good care of your machines, if you take good care of your cars can last more time, right? So it's the same theory. Like if you don't push the limits of your machines because you understand what they do, then you can make them last longer and then work better. So that's also part of the sustainability part. So that's what we're going to talk about today. So we're going to have a case study for an annealing furnace in the stainless steel production line, and Jeremy's going to walk us through. He's going to explain to us a little bit more about that. Before we jump in, I just wanted to say, if Jeremy, if you want to say hi to people, and then if you had anything else to add to what I just said.
Hey, no, Keith, that's a pretty good introduction, actually. So you mentioned everything that can be saved using sustainability-oriented methodology into the full cycles of process for steel. And indeed, most of the savings that can be done here, in steel specifically, it's everything that is in reheating process. Because steel is quite continuous process for raw material, but you have a lot of products that are produced in campaigns and batch. So you produce a piece of steel in hot rolling, so casting, hot rolling. Then you have to store it, maybe to wait that a line is available to process this type of steel. So it goes to the warehouse for 2 or 3 weeks. And then afterwards, when you need to reprocess, you need to reheat again all of this material. So all of these complete steel process lines consume a lot of energy indeed. And if you have, as you say, some problems during the process and you need to reprocess all of these, even if the steel is 100% recycled, you will still lose all the energy that you spent on your process. So it's really what is the most critical, I think, in all of this.
That makes sense.
In steel industry also, we have to be quite constrained with what we do, because steel is something that has mechanical property, physical property, chemical properties. So you can adapt all of these different items in the lines, as you say, but with a certain degree of restrictions. Because if you don't keep specific ranges of temperatures in some sections, you will lose the benefit of the treatment that you are bringing. Like we will speak about annealing of steel now. Annealing is specifically designed to give some more flexibility to steel after it's produced. So it's easier to manipulate afterwards to shape it correctly. But then this requires some specific values of temperature you need to reach. If you don't reach them, of course you lose the annealing properties that you try to give to the steel.
Yeah. There's many different heat treatment sections. So annealing is one. There can be also water treatment.
Water treatment, everything that is gas injection. Yeah. All of these needs to be constrained specific temperature windows. It's consuming a lot of energy as well, consuming different primary materials. And the more you can be sure your production is matching the target in the end, the more you are sure that all of this was not wasted. Indeed.
Okay.
And the reheating, specifically in steel, is happening in every line. So when you produce stainless steel, for example, you have 10 lines of process in series that can be discontinuous. Yeah. And every time you start to process on the line, you need to bring back the temperature of the steel to specific range. So it's a lot of energy consumed there that you don't want to waste.
Yeah, I mean, for this case, for example, you need to maintain an above average temperature of 1,200 more or less Celsius. So that takes a lot of energy to maintain a continuous process 24/7, 365 days a year, the same heat, right? So, but well, I'll let you dive into it, and let's go to the screen.
Here we have a steel annealing process. So this is only the part where you have the actual annealing, because the steel annealing line, of course, is longer than that. You have everything before to uncoil, solder coils together, reheat, and bring the steel back to a condition where it can be annealed. And after the annealing itself, you have several treatments that are still have to be done. So you have a slow cooling, then a fast cooling of the steel to give him the proper properties and ductility. And after you can have also some additional treatments, and again coiling and packaging. This is specifically the section that applies the annealing to the steel. So this one, it's radiant tube furnace. So it means that we inject natural gas or other type of gases in some tubes where the gas is burned, and it distributes the heat homogeneously within the oven with some specific constraints, so you can regulate temperature in different zones in a precise way. So you can correctly reach a temperature profile that you apply to the steel. And that's how we get to this specific profile in step increase of temperatures. So you have this, usually it's big vertical furnaces, because plants are actually quite narrow. So instead of building long lines, they use the same and they build upwards.
So it's a tower, it's a stainless steel tower.
It's kind of a tower, yeah. So you have this annealing section in this, in all of these. The heat is distributed with the radiant tube systems, because you have also some specific gas environment that has to be applied to the surface of the steel. So you need a high level of hydrogen, and you need to keep oxygen level constant as well, to be sure you don't bring some surface defects as well. So the goal is to change the mechanical properties, but we don't want to deteriorate the surface quality. So you need to have this environment, and the tubes protect the flame from being exposed to this environment that is quite explosive, actually. So that's how the heat is distributed. And then on this type of line, then we can collect several types of data. Of course, we have the temperature set points that we can apply in different sections of the system. That will be the ones to apply regarding of the type of steel you process. Okay. So depending on the grade of steel, you have different windows of temperature to operate. If it's thinner, you need, of course, maybe less heat. If it's more thick, you need more heat. It depends on the chemical properties as well. So you have a lot of potential combinations of set points that are already more or less well known because these people are experts in production of steel. And as I said before, the steel is quite constrained process. So you need to be in specific ranges to be sure that your treatment is working.
Okay.
But still, with all of this, in some projects, actually, we noticed that we still have a margin of flexibility in some specific conditions, where it's possible to reduce, even slightly, the temperature inputs, and keep at the same time the same efficiency on the annealing treatment. So we developed this kind of optimization algorithm that is working here for energy optimization, but that would work as well for quality optimization, or yield improvement, or any case that you would like to optimize something.
Okay.
So what the algorithm can do in the background is first, of course, to discriminate different types of steel that can be processed, because different types of steels don't need the same set points. So they will not need the same, and they will not have the same window of temperature that we can decrease to improve the consumption and at the same time keep the quality. So to have that, we need to have data about the process itself. We have data about the steel itself. So we have metadata, like chemical composition of the steel, because it has obviously a big impact on what you can do with it. You have all these temperature set points. You have the gaseous atmosphere measures. You have the gas flow that is currently injected in the system for combustion to generate the heat. And at the end, you have, of course, an inspection system that is consisting most of the time of lab samples or analysis on the ductility of the steels or different reports that can be combined in the application as well. And what we will do is use all of this quality data to create a label on our data on every coil to say quality was good or bad.
Okay.
So this is the first filter that we can use to say to be sure that we will learn things that are useful only when we produce good quality.
Yeah, that makes sense.
We don't want to learn when we produce bad quality.
Yeah, okay.
Or at least we want to learn to avoid it.
Yeah.
So we have all that we need now here. So what I can do is to select all of this data. And we have some embedded functions that we can apply on these. And we will use for this demo this one, so energy reduction function. So you just launch it, you type a name. So I will just give the name of energy reduction, and then I follow the steps. And this is basically the step that would follow a data scientist working on the data.
Okay.
But just in simplified interface, so we don't have to bother with coding.
So theoretically, he would need to understand which sensor is which, from what type of information is sending, and then correlate them between them and the process, and then understand how they have an impact in the overall process. Yeah. So with the app, you can connect everything together and visualize it easily.
Yes, exactly.
Okay.
So this case is quite constrained because it's demonstration data, of course. We cannot use real world data. But indeed, here we have everything that we need because we know from experience that it's what's giving good results. But indeed, you can have maybe 10,000, 30,000 sensors on the line. So it can be the same. You select everything that you need. Of course, if you can restrict a bit the analysis to something that you guess are the most important things to include, it will simplify a bit the work of the algorithm because you will reduce the noise that you bring in the data.
Yeah.
But here, let's say this pre-filtering based on expertise and knowledge from steel producer is already applied.
Okay.
So here you will have only the significant set points, but we can also extract them from a lot larger volumes of data. So here I just make sure everything is selected. I go to next step. I select a time frame in which I want to do my research. So here, to be fast, we will just select 1 day of data. We can aggregate this data. So I will say for that one, I will aggregate data per average on 15 seconds.
Okay.
Because you don't need every one individual second, or even sometimes you have milliseconds data in this type of line. But here it's still quite of a slow process. So you can somehow reduce the volume of data and the repetitivity of the data that would maybe bring noise into the algorithm. So with this, we smooth a bit what's happening to make things more understandable for the algorithm. I click next, then I can filter the data. So indeed, as we said before, we don't want to learn
the quality, no?
Yeah, from bad quality.
Of
so
course.
I will keep only when the production was giving good result. So it was coded in this case in 1 in order.
Yeah, 1 0.
Yeah, binary.
Exactly.
1 is good. Click save. I go to next steps. And here is the final step, which is the most important, is to specify the target you want to optimize and which level you want to reach in your optimization.
Okay.
So in that case, what we want to optimize is the gas consumption, so the gas flow. And I will target a specific threshold. So here you have to trust me with that. But what we identify in the data, maybe we can show if needed as well after. But we look at distribution of data consumption, and we try to place a threshold in a place that makes sense. So we cannot put it too low because it's never happening, or not a few times, and the algorithm cannot learn from that because it don't see a lot of occurrences of these specific conditions. So what we usually do when we start analysis, we take kind of the median of the mean value that we have in the gas consumption, and we just classify when it's below this gas consumption, it's good. When it's above, it's bad. We don't want to use these conditions. And in this case, this threshold in this analysis is 8,800 cubic meters of gas per hour. And I click confirm, and it will prepare all the data and send everything to the data science API that is generating all the intelligence about this. So the algorithm itself, now how it works, it's doing several steps. The first one, of course, it's filtering the data to not have the bad quality. Second steps, the system, because it's organized with a digital twin. So the system is aware of which of the points we selected are set points and which are just contextual information.
So what is the difference between a set point and a contextual information?
A set point is something that you can tune and adapt or change.
You can control.
You can control.
Okay.
While the rest is just information that is tracked, but you cannot directly impact.
Okay, I get it.
The temperature actually is kind of in the middle, because temperature is the consequence of a gas set point. But in most of the case, what we will have is some PID systems in the back where you set your temperature, and the PLC calculate which is the amount of gas to send to reach the temperature.
Okay.
So in some case, like this, temperature can be considered as a set point.
So
Even
like a oven in a kitchen, you put the temperature, and then it's gonna boost the electricity or gas, depending on what you have, to get to that temperature.
Yeah,
okay.
You have these kind of PIDs, controllers, inside the machines or PLC of the machines that transform indeed the signal you give in the actual
I see.
physical phenomenon.
Okay.
So you have this distinction between the points context and the set points. So what it will do, it will try to define if there are different contexts of production with the context information. So in that case, for example, it will use the chemical properties of the steel, the gas atmosphere concentrations, and in this case it will be all. And it will try to see if there are different modes of production in that, because for each of these modes we will need different rules of control. So it's first doing that, trying to discriminate what is the different context is. And second steps, for each of these contexts, we will go through all the data and check if we have some specific combination in chemical composition and gas atmosphere in which we could lower a bit temperature and still having the good quality results because we filter it. So we have a label on the data that this consumption is good or bad. Basically, the algorithm will create some kind of classification between these two and create some rules. It's a bit smarter than rules, but kind of if-else conditions that will say when you have this combination of chemical composition, this atmosphere composition, and this current temperature, you can lower your temperature of a few degrees.
Okay.
Does that sound clear?
Yeah, no, it makes sense.
Good. And here, that's it. The results are generated, so it's taking a bit of time, of course, because it's checking a lot of conditions and fitting some algorithm, different ones. We select the best ones, so everything is done automatically with always the best performances.
So what am I seeing here?
So what you can see here is the actual result of the algorithm. So it will tell you in your period of time that you selected which periods were actually considered as good in terms of gas consumption. So you have it highlighted in green, and you can even zoom on the data and see a bit what was happening. You see here that it's quite flat, but it was a good consumption. And you have actually a lot of signals to investigate together that are not on the same scale. So you see you have the other ones that are here on different scale, where it's difficult to see actually what's happening to the high directly. And when you have these different periods of time, they are higher or lower, it's difficult to interpret.
Yes, so for example, here you see a lot of fluctuation.
Yeah. So then, as I explained before, all of this will be compared by the algorithm. So green versus what is in white here, to find out what was happening in terms of context and at which degree you can reduce your temperatures to optimize the gas. So it detected here two production modes. So you see that the result is explained here. And here you will have for each sensor or each data point that is used for context. So you have chemical composition in carbon, in the nitrogen, hydrogen levels in the annealing furnace, so inside the air of the furnace, and so on. And here you will see that the algorithm detected two production modes based on the grade of steel that were produced. So you see one is high carbon steel, one is low carbon steel. You have other variations in chemical compositions.
Yeah.
And you see that we have also some slight variations in the gas atmosphere that we have. So it means that from there, we have two grades of steel that have to have different recommendations. And we see that some other context variables are also associated to that, meaning that we have still big variations in this, where potentially we could win something playing with the temperature. And what you see here are the two actual recommendations that can be applied for the two production modes.
Okay.
So the first one is called 1, the second one is called 0. That's just a detail because it's kind of agnostic algorithm that have no specific labels. But here, so production mode 1 will be for the steel grade. It was high carbon steel. You will see that it identifies which set points, so it's in the zones 4, 5, and 6, can be adapted and optimized. And here it recommends directly the values that you can apply and target when you set your systems. For the other group of steel, you will have different recommendations in different zones. So it automatically detects which one is the most impactful to at the same time keep quality and reduce as much as possible the consumption. And keep the annealing properties, of course.
Okay. So these are the recommendations. If I would send this information back to the PLC or closed loop it could do it automatically?
Yeah, of course. So what we can do with this system, of course, is to set some targets for production. So we have usually two types of applications for users. Some companies have a policy of manual validation and manual applying the set point.
So from the process engineers and operators?
Yeah.
Okay.
So what they will get is some indicators like this with the target they need to reach.
And they adapt.
Yeah, with the interval of safety they have.
Mm-hmm.
And they have to avoid being in the red, basically, to be sure that they optimize as much as they can.
Okay.
And they can manually apply this if they want to validate it somehow.
Mm-hmm.
But in some other cases, where some customers want full automation.
Yeah.
So in that case, the recommendations that are calculated here are directly sent to the machine.
Okay.
With some safety guards, of course, but it can be done.
So that's what we would call like closed loop AI, basically.
Yes.
Hmm.
And it's what I can show you here, for example. So when you have this algorithm that is generated, it's possible to use in stream. So you will have a specific stream energy reduction here, where actually everything that is needed in context will be provided as input to the model that you generated. And based on this input, in live, the model will recommend all of these temperature set points. So here it's recommending, of course, the target value with some specific windows of tolerance. So you have a lower limit and a higher limit all the time to be sure that you don't overshoot or undershoot.
Yeah. Okay.
So all of this is happening in live, so recommendations come in live, and it can be replicated to control the line. So we have some blocks here to send device commands, for example, that can be used to indeed directly control the machine.
Okay.
And usually what we do in that case, we package this application that is developed here in an image that we publish on-premise, on a system that makes the same exactly execution than here, but locally on-premise, so we don't depend on internet connection.
Yeah, and then basically when it gets connection online, you just get the information back so you can visualize the interface, right? So, which is the next step, right? How do you consume the information, or how do you know if it's working, like how to keep track of it?
Yeah. So as we saw before, we have these boards that can be used to monitor the overall situation of what's happening. Or we have, of course, more detailed information in dashboards. So if you go here and select your annealing furnace, you will have other type of view with other indicators that can be more meaningful for different cases, where you will have all the information you need to assess in detail the situation. So you have usually another view in board and more detailed view here in dashboard. So you see that here it's loading all the data. It was quite a lot in that case. So it detects the type of steel that is processed. So currently it's the low carbon steel with the chemical composition of that. You have here at the bottom the specific temperature in the different zones that are recommended. And you can see here if the people are actually applying the recommendations or not. So here in the green is the windows of time where you can actually optimize something, because the algorithm doesn't recognize all the time. And you see if the blue line is the actual temperature is within the recommendation window, which is the two intervals that you can see here. And with this, it means that you can also track the performance of your system, because you can track when you applied it, where you didn't apply it, and you can generate this kind of simple report where you can compare your overall consumptions of everything that was produced and consumed, and you can identify the specific windows of time where you actually optimize the system, and you get the statistics from that. So you can see here an average hourly consumption that is reduced indeed when they apply the recommendation, which makes sense. And you have here afterwards potential to calculate what is the return of that. So here you see that we saved 1%, a bit more of gas consumption. And you can imagine that is giving big numbers in terms of pricing.
Yeah. Yeah, I mean, each 1%, we're talking about continuous processes that work 24/7 all year round. So 1% can be huge benefit.
Yes. Especially now, so this data might be even outdated.
Yeah.
Because the prices are constantly increasing.
Of course, yeah. Especially so maybe the geopolitical situation can be complicated.
You can even apply ×2 or ×3 maybe pricing on that.
Very interesting. Definitely. I mean, for sure, it's one of the routes that heavy industrials can take today in order to reduce their energy consumption or have a better understanding of what they consume, right? Because first measuring what you consume and then understanding how that happens is the first step in order to first reduce that, right? And once you have that, then you have to start applying the intelligence behind it. And as you said, it can be a bit overwhelming because there's a lot of information. So it's important to tackle one specific challenge first, or one specific asset or process to start with, get some information, get some ROI, and then based on that, you start to replicate, right? So, but from a data science perspective, if you don't have an app like this, how is the process? Very high level, you would have to extract the data from the PLC, for example, and then what you have to create. You start to visualize data and try to identify anomalies, but it's a very manual process, right? And this is for one specific asset. Then to grow, it's more complicated.
Yeah, so what is complicated actually is indeed getting the data and deploy the models that you are building in some usable way.
Okay.
The data science research in the middle is quite complex as well, but everything is more or less standardized. We know that what's important is to prepare the data and transform it in a way that makes sense for the algorithm to correctly capture what has to be captured and provide good recommendations. But this is the usual work of data scientists. The biggest challenge is actually be able to apply these type of models on live, on regular base, on scheduled base, and to maintain this model, make it evolve, because the data is accurate for maybe a period of time, but the equipment's age, so the data is drifting as well. You need to retrain models.
Or the energy prices changes, or there's multiple stuff.
Even the machines, they are degrading all the time.
Of course.
So maybe temperature measures are not as efficient as before. Maybe you have slight variations of different things. And you need to retrain a model to be always fit to be operated. You need to improve the models as well. So with experience, when you track things, you see maybe some specific conditions where you didn't think about before. So you can apply some modifications or improvements on that model. It means that you have to again deploy it after.
Yeah.
Bigger challenge is with this model, how do you bring tangible results to actual operations?
Yeah.
Because it's IT in the end. How do you make something that is quite challenging in terms of IT? IT/OT visible for end users, a process engineer that doesn't have no knowledge in IT or OT.
Yeah, for example, if you show me a huge table of data, maybe you're comfortable with it, but I see it and I'm like, wait, this is too much.
Even sometimes to access this is complicated.
Yeah.
So you need to simplify the access to all the information.
And then we're talking about scaling it up. That's the complicated, right? Like if you do those connections manually for one specific asset or process, you first have to not only maintain the algorithm, but also maintain that the connection and the transmission of information is constant, right?
Yeah, exactly. And then for replicating, it's also very complex because you can have the same asset in different times in the same plant, in different plants. Maybe they will have all different naming conventions for the
sensors or the tags.
The sensor will not be the same.
Or they use different machines.
Different machines, slightly different in terms of value ranges and so on. But somehow here we can facilitate the way as well to templatize all of these. So you can create kind of templates of your assets that will map automatically the sensor that you need based on the digital twin. And it will manage all the models training in the background, all the packaging and deployment on the applications as well.
Okay. So I do have a question, right? Like, let's imagine a scenario where we're talking about a factory floor where there's no data science team. So there's only process engineers and operators. So this type of solution can help them understand better what's happening in the process without the need of working with the data science, right?
Mm-hmm.
Then if we look at another scenario where it's a data science, I mean, what I want to understand is like, this is not replacing a data science, right? Like this is like, how does this work? Is this for you're a data science? Like, is this enabling you to make the job easier? Like, You know, because sometimes people get scared about, oh no, you're bringing AI, it's going to be complicated,
Yeah.
we're going to lose our job. But can you speak a little bit on that?
Yeah, actually, this type of tool is really to reconciliate both the operations and data science. Because for operations, we talked about it before, IT is complex because they don't have training in IT.
Yeah.
So it's difficult to access to this ecosystem, to build graph, build reports, do some small analysis based on the data, to be able to optimize, even without data science or machine learning, to optimize their process based on experimentation. So it's even difficult for them to get data and make their own analysis with state-of-the-art engineering techniques. So somehow with this, they have tools that facilitate the way they can produce this kind of research and analysis. And at the same time, producing some live interaction with all their data in the plant. On the second part, we indeed have data scientists, which will always be needed because this kind of algorithm is working quite well because of the experience that we have embedded in that. But at the same time, it's still a kind of generic approach that can apply to multiple cases. But we can also push the results even a bit further if we have a bit more customization of the algorithm itself. And there, data scientists will have all the tools again to get all the data directly, because again, it's combining different data sources. It's not only extracting from an historian or PLC. You may need quality data, maintenance data, a lot of things. So all of this is already centralized, so you can just get it and start your analysis. And secondly is that you can go a lot deeper in the analysis with different tools. So if you have, most data scientists will work in Python, but some of them will work with machine learning platforms that are simplifying also the way they work. And that can be really powerful to use in specific cases. So what data scientists will have is a set of tools that can be connected to the data sources that we have here and build his own algorithm and put them in production using the application as well.
I see.
So it's facilitating also the way that we just use the analysis that we do and put it somewhere in production in an integrated environment. And after, of course, to manage the retraining and the scaling and the replication. Because all of this is a lot of work that is maybe less fun for data scientists. Because when an algorithm is done and it's working, usually the job is done.
Yeah. That's very interesting, Jeremy. So I think we're coming up to the end of our session. In any case, if there's any open questions or there's some questions we didn't answer, obviously you can feel free to reach out. We'll jump on a call and we'll be happy to show you more in detail what we do and also show you some case studies of other industries of how we work with our clients today. All in all, thank you for joining. Hope it was very informative, and thank you, Jeremy, as well for your time and your expertise.
My pleasure.
Catch you on the next one. Ciao.
See you.